So this is the last part of section 5.1, and it's specifically about financial models. We have an example here. It says on January 1st, 2015, an investor put $2,000 into an account paying an annual rate of 4.25% compounded monthly. So there's a new term. Find a model that gives the dollar amount A in the account T years after January 1st, 2015. So if it weren't for the compounded monthly phrase, this wouldn't be too bad, right? If it didn't say compounded monthly, and I was to just take that out just for a second, then my model would be A of T is $2,000, and then we have a rate of 4.25%, so that's 1.0425 to the T. But this is not compounded monthly. Okay. So unfortunately, that's not what we have. So let me get rid of that because we do have the compounded monthly. All right. So what does this mean? Let's get into some more financial terminology. First, we have to look at the APR. So the annual percentage rate, which is also called the nominal rate. Those are the same thing. The APR and the nominal rate are the same thing. That's what our 4.25% is. So really, 4.25% is not the growth rate. It is the APR, which is confusingly very, very close to the growth rate, but not exactly the same thing. The annual growth rate, I mean. Although I think sometimes the terminology does get confused. Anyway, that this rate is compounded monthly, what does that mean? It means that each month the account earns 1/12 of the APR. So if we think about our monthly growth factor, what's that going to be? Well, we take 1/12 of the APR and we add that to 1, and that is our monthly growth factor. So how do you convert a monthly growth factor to a yearly factor? Well, to go from monthly to yearly, we raise something to the 12th power. So we take this value and we raise it to the 12th power. So then this thing that's setting inside here, that is actually my regular growth factor, B. And just like in the normal exponential model, A times B to the T, we have our A, we have our B, and then we have T, so A times B to the T. And then we can simplify this somewhat by putting these two, multiplying them together, simplifying this exponent. And there we go. There is our model for the compounded monthly. And it really all came down to understanding this statement right here that says that compounded monthly means that each month the account earns 1/12 of the APR, and then using that to get my monthly growth factor. So we can generalize this idea. And I'm going to go ahead to the slide in which we do that and look at the general compound growth formula. So this is a big one. This is very important for exponential modeling, for financial stuff. So here it is. The amount of money after T years in an account earning interest compounded N times annually. So in the example we just did, it was monthly, compounded 12 times annually, so compounded monthly, is given by the exponential function A sub 0, and really this is the one you're going to use, is over here. A sub 0 times 1 plus APR over N to the NT. APR is the nominal interest rate, and then we compound it however many times per year. All right, so this is a big formula. You do need to memorize this. Now let me go back and let's answer some questions about this model now that we have it. So there's our model. And here's a few questions. First of all, what's the account's annual growth rate? Okay, so that's that annoying thing that I said earlier. The APR was close to the annual growth rate, but not exactly the same thing. So the APR is that 4.25%, right? 4.25%. Sorry. APR is 4.25%. The annual growth rate, how do we get that? Well, we need to go to our model, and we get the factor, which is this. And so actually, let's do this on the whiteboard. So my factor is 1 plus 0.0425 over 12 to the 12. That's my factor. And then to convert this factor to a rate, we subtract 1. And then to convert that to a percent, we multiply all of that stuff by 100. And so you do have to put all this in your calculator. So let's do it. My general method here is I kind of work from the inside out because there's a lot of parentheses and a lot of fractions and so forth. So this is what I tend to do. And I screwed up. 0.0425 divided by 12. I get that. Then I add 1 to it, which is this stuff right here. Then I raise that to the 12th power. Then I subtract 1 from that. That's my rate right there, and then multiplied by 100 gives me my rate in percent form, so it's 4.33%. So this is R. So notice APR is 4.25%, but annual rate, growth rate, is a little bit higher, 4.33%. This actually has yet another name. You may have noticed it on the slide. Let me go back to that. So the other name for this is called the effective annual yield. So leave it to financial stuff to have many different names for the same thing, right? So we'll talk more about the effective annual yield idea later, but the basic idea is that this APR stuff is confusing and we want to turn it into a more standard form, and the more standard form is the effective annual yield. And so that's 4.33%. Okay. More questions. In what month and year will the account balance reach 2,500? So that's going to be a calc intersect question. We will take our model. That's going to be Y1, and Y2 will be 2,500, and then we do the intersection. That's what you see happening here. There's really nothing new in this. It's the same sort of procedure that we've done before, but you certainly should make sure you can do it. Probably the main difficulty is typing in all this stuff into your calculator correctly. And then we use the table to figure out our x min and max, and then we do zoom fit and find your intersection. Okay. Question C, how much is in the account on January 1st, 2025? Well, this is going to be a vars y vars question. So essentially what we want to do is evaluate the model. I forgot when we started actually. We started in 2015, January 1st. So that's 10 years. So we're going to evaluate the model after 10. So whatever that is. Again, really nothing new in that. So I would like to make sure that you can do that, and you should definitely try it. I'm not going to do it right now though. Finally, what is the account's doubling time? Once again, this is the same sort of question that we've had before. Let me skip to that. And what I would do here to find the doubling time, actually let me go back, is I would take my model, enter it into y1. We certainly haven't used it already a bunch, so it should already be there. And then for y2, we're going to double our initial value, which was, I believe, 2,000. Yeah. So we'd have 4,000, and we want to know when we get to 4,000. So it's basically the same steps as what you did here to find the doubling time. All right, so the actual questions, except for this first one, are all pretty straightforward. Okay. So getting back to that effective annual yield thing. So this slide says extracting the growth rate, but what we're really dancing around here is the terminology effective annual yield, which I will probably call EAY from here on out. So the point is that the effective annual yield and the growth rate are the same thing. These are synonymous. And to find the growth rate, what do? Well, we basically isolate the factor, which is all this business in here. So we get the factor, and we forget about a sub 0, we forget about the variable t, and we just look at the factor. That's b. And then to recover the rate from the factor, just like we always do, we subtract 1 from this, and then to put it in that in percent form, we multiply it by 100. So this formula right here is your EAY formula. And I think I have that on the next slide. Yes, there it is. Okay, so here's the formula down here, and it's the same one that we were just looking at. But what does this mean? Why do we call this the effective annual yield? So if you think about that word effective, you can sort of imagine that this said equivalent. So it's sort of effective in that sense. Like, what do you actually get effective? So an investment's effective annual yield is the rate that would yield the same amount of interest if interest were compounded annually. So basically, it's sort of like you come in, you have some interest rate that has some weird compounding time, like I'm going to compound it every 15 days. And so when you tell me that I've got a 7% interest rate compounded every 15 days, I don't really know like if that's good or bad. You know, I don't because that compounding every 15 days thing makes it a bit confusing. So basically what this is saying is like, hey, can you tell me, can you take that 7% compounded every 15 days or every month or whatever, and figure out what an equivalent one-time annual interest rate would be that you would just do once per year, like we used to do, like in previous sections. Okay. So that's what we mean by effective annual yield. And it gives you basically a way to like measure things. So here's an example of that, of measuring. I've got 3 different accounts. And one is, they all have different APRs and they all have different compoundings. So we have an APR of 5.05 compounded quarterly. We have one 5.1% compounded annually, and then 5% compounded daily. And I want to know which one's the best and which one's the worst. So to answer this question, I need to compute the EAY for each one. So 3 different EAYs, and that formula is 1 plus APR over N to the N, no variable, minus 1 times 100 to put it in percent form. And really, you just plug and chug. You just use this formula 3 times. And that's what you see here. So we just run this formula 3 different times, and then we pick the best of the 3. All right, I think I'm about out of time with this video.